Namaskar students. In this lecture we will discuss interpolation error in higher degree polynomials. Let us assume that we have n plus 1 data points x0, x1 xn. These are n plus 1 distinct data points in the closed interval a comma b, and f we are assuming as continuous function in this interval. Also we are assuming that f has n plus 1 continuous derivatives in the open interval a comma b. Then the theorem states that for each x belongs to a comma b, there exists a xi belongs to a comma b such that the error, we have to write the expression for the error such that this fx minus pnx, this is nothing but the error, so is equal to f n plus 1th derivative at xi divided by n plus 1 factorial and the product of I equal to 0 to n x minus xi. So this is the formula we need to derive for interpolation error in nth degree polynomial. So just quickly revise once. We have n plus 1 distinct data points in the closed interval ab. F is a function continuous in closed interval ab, and it has n plus 1 continuous derivatives in this open interval. Then for any x belongs to a comma b, there exists a xi belongs to this interval ab such that fx minus pnx is given something like this. So this we need to prove. This is the interpolation error for nth degree. So we denote this as ENFX. We also denote this as this. So this equal to this we need to prove. So let us try to prove. How we will prove this? The logic in proving this will be same as we did for the two data points. So here also we start with the interpolation condition. So En, if we are interested in ENFX, so this will be equal to 0 at x is equal to xi, because at x is equal to xi the functional value and the value provided by the interpolating polynomial must be same. So error will be equal to 0, and this will be true for all I equal to 0, 1, 2, n. Then for any x belongs to this interval a comma b, and we assume x is not equal to xi, we define a function gt. This kind of function we have already defined for two data points. So similar function we are going to define here also. So ft minus here it will be pnt, we can name pnt, and minus this will be fx minus this pnx. In some books pnt is also written as pt, n is not mentioned. So you may write it, you may not write it, it depends, right? So this fx, so this, and with this the multiplication factor is t minus x naught, t minus x1 t minus xn whole divided by x minus x naught, x minus x1 x minus xn. This is the similar function we have chosen for two data points. The same has been generalized over here for n plus 1 data points. So we name it as equation number 1. Now here also, as there we observe that, what we observe here also, we observe that this gt will be equal to 0 at gt will be equal to 0 at t is equal to x, and t is equal to xi for all I equal to 0, 1, 2, n. So we have this. So again what we are going to do, as done there, we apply the Ross theorem repeatedly. There we have applied twice. So here we will apply the Ross theorem repeatedly for we will apply for GT, G dash T, G double dash T, and dot dot dot, continuing on similar line, G and T, nth derivative. So we will apply Ross theorem repeatedly for this, and we obtain from there we obtain G n plus 1 xi equal to 0, where xi is some point. We obtain G n plus 1 xi equal to 0, where this xi is some point such that minimum of x0, x1 dot dot dot, xn and x should be less than xi, and it should be further less than maximum of x0, x1 dot dot dot, xn and x. So likewise here also we will differentiate the equation in which we have considered the function. We have named it as equation number 1. So here we will differentiate that n plus 1 time with respect to t, and from there we can get Gn plus 1 t will be equal to Fn plus 1 t minus, here we will get factorial n plus 1, and this is fx minus pnx, and some of px is also taken, and we will get here x minus x0, x minus x1 dot dot dot, x minus xn. So this we will get. Let it be equation number 2. Now equating these two equations, here it is equal to 0 and here we are going to get this. So using this over here and simplifying it for fx, so we get, after doing this procedure, we get fx is equal to px plus x minus x0, x minus x1 dot dot dot, x minus xn whole divided by n plus 1 factorial, and together with this multiplication we get fn plus 1 of xi. So taking this over this side, I am again doing over here only. So we get this fx minus px or pnx, whatever you want you can write. So both are used in some books pnx and some books px. So here also I might be using pnx somewhere and px, so but you use uniformly, either use pnx throughout or use px throughout. So this minus this is coming to be like this. So this is nothing but this is the amount of error. So finally we conclude that this is En fx is equal to this. You can write in the form which is given in the question like this. This is over here. It means it is in multiplication factor. So this is coming out to be just wait, I will write here only. So finally we get this error as fn plus 1 xi by factorial n plus 1, and that we can write as product of I equal to 0 to n x minus xi. So this what we wanted to prove. This is the truncation error in the Lagrange interpolating polynomial of degree at most n. So here also likewise we have find for the two data points. We can go further and discuss many more things regarding that, but this is all about the truncation error that we are obtaining for Lagrange polynomial having degree at most n. Thank you.